Welcome to Quantum, a channel dedicated to theoretical physics, with all its rigorous mathematical underpinnings and profound philosophical implications.
In today's lecture, we explore two of the most remarkable features of the fractional quantum Hall effect: fractional charge and fractional statistics. The lecture is divided into three parts, each building on the last. First, we begin with the Hall conductivity for the FQHE with quasi-holes. Here, we show how inserting magnetic flux through a Corbino ring creates a quasi-hole at the center of the droplet. This process transports a fractional amount of electric charge from the inner to the outer edge. By analyzing this transport, we derive the Hall conductivity and confirm its fractional quantization. Second, we introduce the Berry connection in the FQHE via the plasma analogy. In this section, we reinterpret the many-body wave function as a classical plasma. Quasi-holes appear as impurities, and their interactions with electrons in the background field shape the system's geometry. This analogy allows us to compute the Berry connection explicitly and extract the topological structure encoded in the wave function. Third, we examine Anyon's fractional charge and fractional statistics. Using the Berry connection, we show how a quasi-hole accumulates a geometric phase when moved along a closed path, revealing its fractional charge. When one quasi-hole loops around another, we find a second phase contribution, the statistical phase, which proves that quasi-holes are anyons, particles with statistics interpolating between bosons and fermions. Together, these three parts reveal the deep connection between geometry, topology, and emergent quantum behavior in the fractional quantum Hall effect. Hall conductivity for the FQHE with quasi-holes. In the fractional quantum Hall effect at filling fraction 1/m, the Laughlin wave function describes a highly correlated, incompressible quantum fluid. Quasi-holes are localized excitations that puncture this fluid and modify the wave function. Despite appearing as excitations, they belong to the same topological ground state sector as the Laughlin state. These sectors are not distinguished by energy or any local observable, but by global topological features. Quasi-holes represent non-trivial configurations, akin to instantons, and are connected to the Laughlin state via operations like braiding or flux insertion. The key insight is that this is not a conventional phase with symmetry breaking, but a topologically ordered quantum fluid. Next, to probe the Hall response, we place the system in a Corbino ring and adiabatically insert a magnetic flux through its center. This doesn't exert a force but shifts the quantum phase. As a result, the system evolves through spectral flow, staying in the ground state but acquiring a quasi-hole at the center. This process causes a fractional charge to move radially from the inner to the outer edge of the droplet. Inserting one flux quantum transports a charge of -E/m. From this, we deduce the Hall conductivity. It remains quantized at a value inversely proportional to m, a direct signature of the topological nature of the fractional quantum Hall state. Berry connection in the FQHE via plasma analogy. We begin by considering a fractional quantum Hall droplet that contains several quasi-holes located at fixed positions. The quantum state of this system depends on those positions, and its normalization defines what we call the partition function. To compute it, we use the plasma analogy. In this picture, the modulus squared of the wave function, which gives us the probability distribution, is mathematically equivalent to the Boltzmann weight of a classical two-dimensional plasma. In other words, it looks like the exponential of minus a potential energy, exactly as in statistical mechanics. Here, each electron in the quantum fluid behaves like a point charge of -m, where m is the inverse filling fraction. Each quasi-hole appears as a negative impurity with unit charge. And finally, the system is neutralized by a uniform positive background charge, which originates from the external magnetic field. This mapping turns a quantum problem into a classical one, a system of interacting charges in thermal equilibrium. Now, why do we care about this partition function? Because it allows us to compute the Berry connection, a geometric quantity that tells us how the wave function changes as we move the quasi-holes. In more formal terms, The Berry connection is defined as the overlap between the wave function and its derivative with respect to the quasi-hole position. This captures the phase acquired during adiabatic transport, that is, when a quasi-hole is moved slowly in space. But this expression involves the derivative of the normalized wave function, which brings in the partition function. In fact, the Berry connection ends up being proportional to the derivative of the logarithm of that partition function. So in order to compute the Berry connection, we need to understand how the partition function depends on the positions of the quasi-holes. At this stage, we invoke a key physical principle, screening. In the plasma picture, when the parameter m is not too large, the system behaves like a disordered Coulomb fluid. In this regime, the electrons rearrange themselves to fully screen the electric fields of the quasi-holes. This is called full screening. It means that, to an observer far away, each quasi-hole appears electrically neutral. The surrounding electron cloud perfectly cancels its charge. As a result, the partition function becomes independent of the quasi-hole positions, at least to leading order. This simplifies the problem immensely. However, two important corrections must be introduced to accurately account for the plasma partition function. First, the impurities themselves carry negative charge and repel each other. This produces a logarithmic Coulomb interaction between their positions. Second, each impurity feels an attractive force from the uniform background charge. While electrons are attracted inward, the quasi-holes tend to be pushed outward. These two effects modify the partition function and must be taken into account in the Berry connection. With this understanding, we now compute the Berry connection. Because the wave function is holomorphic in the quasi-hole coordinates, and the partition function captures all the non-trivial geometry, the Berry connection reduces to a complex derivative of the log of the partition function. The result contains two terms. One term arises from the repulsion between quasi-holes. It behaves like a gauge field sourced by the other impurities. This reflects their fractional statistics. The second term grows linearly with the position of the quasi-hole and comes from the interaction with the uniform background charge. Together, these terms describe how the geometric phase, and thus the topological structure, depends on the configuration of the quasi-holes. This is a central result of the fractional quantum Hall effect. It shows that the Berry connection is not just a mathematical abstraction, but a real, measurable quantity encoding the topological response of the system. Anyon's fractional charge and fractional statistics. To compute the fractional charge of an anyon in the quantum Hall droplet, we analyze the Berry phase accumulated when a single quasi-hole moves along a closed path that does not enclose any other quasi-holes. In this case, only the second term in the Berry connection contributes, the one that arises from the interaction with the uniform background charge. This term is linear in the quasi-hole's position and reflects the smooth, radial effect of the background field. By integrating this connection along the path, we obtain the Berry phase, which corresponds to the Aharonov-Bohm phase accumulated by the quasi-hole as it encircles a region threaded by magnetic flux. Using Stokes' theorem, this phase turns out to be directly proportional to the enclosed magnetic flux, and from it, we identify the effective electric charge of the anyon. The result is striking. The anyon carries a fractional charge equal to -E/m. This confirms our earlier physical interpretation. The quasi-hole is not just a localized absence of charge, but a topologically meaningful excitation carrying a fraction of the electron's charge. We now move to the second defining feature of anyons, their fractional statistics. To uncover this, we consider a different situation. This time, one quasi-hole, say the first, performs a closed loop around another quasi-hole, say the second. In this configuration, both terms in the Berry connection contribute. The second term again gives the Aharonov-Bohm phase and reflects the quasi-hole's fractional charge. But the first term, which depends explicitly on the relative positions of the quasi-holes, now plays the central role. This term leads to a geometric phase that depends only on the topology of the path, the fact that one quasi-hole wins around another. Evaluating the Berry phase in this setup, we find that the wave function acquires a phase factor of 2 pi over m. This is not just a conventional -1 or +1 as for fermions or bosons. Instead, it represents a fractional phase, an angle that lies between the familiar bosonic and fermionic cases. From this, we extract the statistical parameter denoted alpha, and we find alpha equals 1 over m. This means that the quasi-holes in the fractional quantum Hall effect obey anyonic statistics, interpolating smoothly between bosons and fermions. Let us take this further. Suppose we now consider a composite object made of k quasi-holes. If we exchange two such composites, the total Berry phase is proportional to the number of individual exchanges, that is, k squared. As a result, the corresponding statistical parameter becomes alpha equals k squared over m. In particular, when k equals m, the composite carries a statistical parameter of m, meaning that the object obeys fermionic statistics precisely when m is odd. This shows that a bound state of m quasi-holes behaves exactly like a single electron. It carries the right charge, and it has the right statistics. This beautifully unifies the picture. The electron emerges as a topological composite of fractionalized excitations. That concludes today's lecture on fractional charge and statistics in the quantum Hall effect. If you enjoyed this content, don't forget to like, share, and subscribe to Quantum, where we explore the deep structure of physics, one idea at a time. Feel free to leave your thoughts or questions in the comments. Thanks for watching.